Hello, relativity friends. I was perusing the internet. I found this quote. The elegance of the Einstein field equation ensures that they hold a special place in the hearts of many physicists. However, any fondness you may feel for these equations will be severely tested if you ever try to solve them. This is by David Tong, Professor David Tong at Cambridge University. This is exactly how I feel about general relativity. When I first started studying it, it was so elegant, so beautiful. And then you try to solve the equations and you're like, oh my, what kind of schmuck like me with pencil and paper do at home? I don't have a supercomputer. Anyway, that's not the point. I just thought that was cute. I was perusing my book, General Relativity and Intuitive Introduction, the chapter called General Relativity for Dummies, and I saw this drawing he made. And I said, the geodesic equation, which we've been working on, and he multiplied both sides by mass. And then this is the second law of motion from Newton, and you just look at them and they start looking very similar. And then you say, oh, how can you make this look like that? So that's what this is about, okay? So the first thing I needed to do was understand this. Either I've never seen it or I've forgotten it because I haven't been in school, as I've said many times, in a very long time. So what we need to do is find the weak field limit of the geodesic equation. So this in a weak gravitational field and something moving slowly, it should become Newtonian. That's the point of this exercise. Okay? Excuse me. So we want to start with time. There are two types of time dilation, gravity and velocity, or both. You could be having both types of time dilation. As we do in real life, our GPS satellites that are zooming around Earth experience both gravity and velocity time dilation. Okay, we learned in special relativity that time is not a constant, right? So we looked at this equation the other day. So we said this t, called coordinate time, times this factor, the factor, is equal to this t tau, called proper time. So as an example, this would be the time of an observer stationary on Earth, and this would be the time of someone zooming around in a rocket ship. All right? So I asked this question to Google. What's the fastest humans have ever gone? And here's the answer. It's about 40,000 kilometers per hour set by the crew of the Apollo the 10 in 1969. I won't tell you how old I was, but I saw this. Okay, so I'm going to take this number, convert it to meters per second, and plug it in this part of the equation, okay? So here is the velocity. This is v. Here's the speed of light. I square them both, and I do the division, and I get this unbelievably small number, which looks even more terrible when you write it out like this. So 1 minus this teeny weeny number is basically 1, right? So that means that t equal tau. So the coordinate time equal the proper time in what's called the weak field slow moving limit. All right. Now here is the gravitational time dilation. This is an approximation of the equation. All right. So we got the gravitational constant, mass of the Earth, the radius of the Earth. No, I'm sorry, the radius to wherever this is, and the speed of light squared. So let t be the elapsed time on Earth, and tau be the elapsed time on the International Space Station. Okay? So we plug these numbers in, and here is the gravitational constant. Here's the mass of the Earth. Here is the distance from the center of the Earth to the International Space Station. The center of the Earth to the International Space Station. The speed of light squared. And once again, we get this teeny weeny number. So it just makes no difference. So once again, tau equals t. So time equals time. And in Newtonian physics, there is only one time. Okay? So we need to understand what is the gravitational potential phi. So at a point, it is the gravitational potential energy, U, per unit mass at that point. Okay? So we're moving a unit mass in a gravitational potential, right? So basically, so you can express it as phi equals U over m. So basically, we're doing work, right? We're moving a unit mass in a potential. So what is work? It's the force times displacement, okay? And what is force in the Newtonian world? It is this equation, which is not a tensor, which is not a vector equation. So we need to make it one just by adding r hat. And dr we're going to express like this, dr times r hat, so that we have a proper tensorial equation. All right, so we write it all out. We bring these constants out front. We bring the scalars in front of the vectors. We dot these. That's just one. We integrate this from infinity to r. Now, what's that mean? Okay, so here is the Earth as an example, and you're coming in from infinity. So you're doing the work needed to push that unit mass all the way from infinity to some mass. So that the big M is Earth, the little m is that unit mass that's coming along. Okay, so we solve this equation. We pick up a negative. Is that right? I think it is. Like this. So then the phi now is defined as U over m, so it's just negative gm over r. You don't really need to even know this. I just needed to know what that was and where it came from. That's the point that I'm doing here. Now, for a conservative force like gravity, the force can be expressed as the gradient of the potential energy. We just found that upstairs there. So it looks like this. So force is equal to negative the gradient of the potential energy, and we found this relationship. So U is equal to phi m, right? So we put that in. And so we have this equation. Well, we also know that force in Newtonian physics is mass times acceleration. So we can write now the acceleration as the change in velocity with respect to time. So the masses, they cancel, which is equal to negative the gradient of phi. That's the gravitational potential. Why does that phi look different than that one? Anyway, okay, and now we can express the velocity as the second derivative of position with respect to time, and we have this equation. Okay, now let's change x and the del operator to their component form. So it would be xi over t squared, the derivative of t squared, and this would be the partial derivative of phi with respect to xi. So these two things are the same. This is just in a general form. This is in the component form. All right. So now we have something here that looks like this, right? So here's the geodesic equation. So Einstein's equation of motion, and here's Newton's equation of motion. Now this looks a lot like that, but this doesn't look at all like this, right? So the first thing we can do is say, hey, we just said that tau is equal to t, right? In the weak field slow moving limit, there needs to be an acronym for that. That tau is equal to t. So we can replace that already, okay? And we get this far. Now for the next section of this, I'm going to hand you over to Chris, who does, and I've been reading this all day on different places, different books. He does the best job I've seen. So rather than me reinvent the wheel, I'm going to hand you over to him. Okay, here we go. This is Chris, his general relativity playlist, Relativity 107D. And he is just now at the point where this is what we just got through doing. This is the geodesic equation. He's getting ready to replace this parameter he had in here called the lambda with time. Okay?
First, we choose the path parameter lambda to be the universal Newtonian time coordinate t. Next, let's see what we get when we take the sigma index to be 0. Now, in previous videos on special relativity, I've said that the x0 coordinate is just the speed of light times t. But since we're dealing with Newtonian gravity and Galilean relativity, we're going to say that the x0 coordinate is just the standard time coordinate t, without the factor of the speed of light. So the second derivative of t with respect to t is just 0. Since this term is always equal to 0 regardless of the spacetime coordinates, this implies that the connection coefficients with 0 as an upper index must always be 0. So the upper indices for the connection coefficients are only non-zero for the space components 1, 2, 3. Now the first terms match, but let's look at the second terms. The original equation has no velocity terms, no first-order time derivative terms for the spatial components.
Okay, this confused me when I first watched it. When he said the original equation, he means this. Do you see? There's no velocity terms in this. That's what he's talking about. Okay?
This means that the connection coefficients with spatial lower indices 1, 2, 3 must all go to 0. So we're left with only the connection coefficients that have 0, or time, in the lower indices. Now, comparing these terms, we can deduce that gamma I00 must be equal to the partial derivative of the potential by partial xi. This is because the x0 coordinate is just t, and so these two derivatives each become 1, and we're left with our original equation. So
there you go. I thought that was excellent the way he did that, and it answered all my questions. All right, I'll see you later.